Let's take a look at section 5.3, Properties of Logarithms. These first three properties are based on the rules that b has to be greater than 0, b cannot equal 1, u and v represent positive numbers, and r is any real number. These three rules are very closely related to exponent rules that you're familiar with. I like to refer to them as the three amigos, because when we use one in a problem, chances are you're also going to use at least one of the others as well. So the first one is referred to as the product rule for logarithms. We have log base b of a product is equivalent to log base b of u plus log base b of v. Notice they took a product and wrote it as a sum, an addition. Remember the exponent rule that says when you're multiplying product, multiplying bases, you add the exponents. Use that to help you remember that this multiplication will become an addition. Then we have the quotient rule for logarithms. Log base b of u divided by v is equivalent to log base u minus log base b of u minus log base b of v. Notice that the quotient became a subtraction. Remember the rule for exponents that says when you're dividing bases, you subtract the exponents. So we have 5 minus 2. Well, this quotient became a subtraction of the individual exponents. Remember, logarithm is an exponent. Then we have the power rule for logarithms. Log base b of u raised to the r power is equivalent to r times log base b of u. We're saying take this power and multiply it times this power, which, remember, this is an exponent. So r times this. So we have one exponent multiplied by another. Well, remember, when you have a power to a power, the rule is multiply those powers. Well, this here, log base b of u, represents an exponent. We're saying, okay, take this exponent and multiply it times this. So we have an exponent to an exponent, we multiply. All right, take a look at these common mistakes. People try to take these rules and get creative and use them in these categories, in these situations, and it does not work. The first type of problem that you're going to encounter is something like this, where they want you to use one of those three rules to expand the logarithm. So you are given a single logarithm and they want you to expand it as a sum, difference, or product, as we see up here. So taking this and realizing these are the three rules we're working with, we have a product. We can rewrite that as the sum. So we have log base 4 of x plus log base 4 of y. In this one, we have a quotient. We can rewrite that as a subtraction. So log of the numerator 9 minus log of the denominator t. All right, here we have a power to a power. So we're going to use this rule and multiply. So we bring that exponent of 3 in front and multiply it times the log base 5 of y. All right, in this example, we have a product again, so we're going to rewrite it as a sum. Log base 3 of 27 plus log base 3 of w. Now, before we turn this in as our answer, we pause because you can actually calculate what this is without a calculator. What is the exponent that I have to raise base 3 to get 27? And the answer would be 3. So this reduces down to 3, and they expect us to do that and turn this in. All right, taking a look at this one, we have not only a product, 5 times e, but we have a raised to a power. So we're going to first use the product rule. So we break it up, natural log of 5 plus natural log of e to the second. Then I can take the third rule, the power rule, and take this in front and multiply. So we have 2 times natural log of e. Then I could actually simplify the natural log of e. What is the exponent that you'd have to raise base e in order to get e? Well, all of that equals a 1. 2 times 1 is 2. Here's our final answer to turn in. All right, here's another example where we're being asked to expand the single logarithm. So notice here we've got all three properties can be used because you have a product in the numerator, you have a quotient, and you have powers to power. So we're going to first use the quotient rule and separate it as a subtraction. So we have log of the numerator, natural log of the numerator minus natural log of the denominator. Then breaking up this product into a sum, we have natural log of a squared plus natural log of b to the third. All right, then using the third rule, the power rule, we're going to bring these exponents in front and multiply them for each of these. So we have expanded it as much as we possibly can. All right, so the next thing they want you to do, use those same rules, but this time take the logarithms that are already expanded out, separated, and bring them together using those rules as a single logarithm. So what we're going to do is, looking at this example, we need to first remove these 2's. So we're going to use that third power rule to do that. Rewriting this as x squared, rewriting this as y to the 1/3, or remember, you could also write that as the cube root of y. If you recall, when you're dealing with rational exponents like x to the 1/n power, that is equivalent to the nth root of x. So x to the 1/3 is equivalent to the third root of x. The denominator becomes the index, the numerator becomes the exponent. All right, so back to this example here, you could write it as the cube root of y. So now that we have a sum, we can rewrite that as a product. Remember the first property we went over. And so this would be our final answer. Notice we went from 2 separate logarithms to a single logarithm to turn in. All right, we have the logarithm property of equality, which basically says when you have the same bases, log of this, log base b of u equal log base b of v, same bases on both sides, single log here equal a single log here, you can drop the logs and say that the arguments then have to equal each other. Or if you have an equation, you can take the same base, the same log of both sides. We're going to use this property of equality in both directions. Sometimes it'll be to our advantage to bring the logarithms together and drop them. And at other times when we have exponential equations that we're not able to relate the bases, we can take the log of both sides and then use those 3 properties, the 3 amigos that we just went over, to help us solve the problem. So we're going to use it in both directions. Now you may recall there are certain times in algebra where you have to check your answer to make sure that you end up with a true statement, a true answer, and not an extraneous solution. One of those times is when you have fractions in your equations, because you might generate an answer that makes the denominator 0, which makes the problem undefined. The other time is when you have even roots, even radicals like square roots, fourth roots. You need to make sure that the quantity under the radical sign is greater than or equal to 0 and not negative, and otherwise you'd end up with a complex number, an imaginary unit. And so those are 2 times where you have to check your answers to your equations. Well, you can now add a third time. That third time will be anytime we are solving a logarithmic equation, we must check to make sure that our answer is valid. If you remember when we first defined the logarithmic equation, we said that the argument must always remain greater than 0. So when we come up with our final solution, we'll need to check by plugging it into the argument to make sure that it stays greater than 0, that it stays positive. So take a look at this first example here. Using the 3 amigos, one of the things we want to do to be able to get to this place of having a single log on both sides is we want to bring the logs together. So using the 3 rules, properties we went over, we're going to first use the power rule and rewrite this one, bringing the 2 over here. We're going to use the product rule, which says we can rewrite this sum as a product. And so combining that, we get this. Now we have the same logs on both sides, and we have single logs on both sides. So we can drop the logs according to this property here and set the arguments equal to each other and then solve. I can use the square root property to finish this off, remembering to put plus or minus, and we end up with the fact that x plus 5 is equal to plus or minus 6, subtract the 5 from both sides, and we have 2 possible answers, negative 5 plus 6, which is 1, or negative 5 minus 6, which is negative 11. Before I turn both of these answers in, I need to look back at the problem and see if either one of them would make my argument be negative, because I would have to then not include that. So notice if we let x equal 1, we get 1 plus 5, which is 6, which is greater than 0, no problem. But if I let x be negative 11 plus 5 would be negative 6, which makes the argument negative, which is not allowed in this function. And so we have to eliminate that as a choice and only turn in 1 for our answer. So there's an example where we use the three amigos, those properties, as well as the property of equality to solve. Now, you're also going to have situations where you are given a certain base, like here, base 4, base 7, and so forth, and your calculators may not be set up to calculate those bases. Some of them are, but many of the scientific calculators are only set up to calculate based on the common log, base 10, and the natural log, ln, base e. And so we have a change of base formula that allows you to change from one base to any base you so desire. Of course, we'll be changing it to common log or natural log so that we can type it into our calculators. And so here's what you would do. You would take what they're giving you and rewrite it as log of whatever base you choose to the argument, your original argument, and log base to the original base. So notice I'm changing to base A. I'm going to put the original argument on the numerator, and I'm going to put the original base here in the denominator. So I like to say to change the base, you are going to have the argument over the base. So looking at this example, log base 4 of 51, we would rewrite this as log, common log 51, so that's the argument, divided by common log 4, or natural log 51 divided by natural log 4. You'll notice I have these red parentheses to emphasize that they need to be a part of what you type into your calculator. Many of your calculators will start you off with the first parenthesis. You just have to remember to close them off. Parentheses will be your best friends in this chapter. So go ahead and try plugging these in and see if you get this answer. We are asked to round to the 4th decimal place, so we always look one place over to determine whether or not to round up or down. So because this was a 1, we're going to round down to 2, and there's our answer to turn in. All right, here's an example here where they ask us to use the change of base formulas and the properties to rewrite these as a single logarithm with the indicated base. So they want us to rewrite these, which is base 3 and base 9, all in terms of base 3, and then also bring it together as a single logarithm. So taking a look at this over here, writing the problem over here, the first thing I did was take the 4 and rewrite it as an exponent. So we have w to the 4th power. Then using the change of base formula, then we rewrote this in terms of base 3. So we have log base 3 of the argument, w to the 4th, over log base 3 of the original base 9. Then I realized we could simplify this as just a 2. So that 2 then could be written in front of this as just 1/2, a coefficient of this logarithm. We could then take that, and using the third property of logarithms, we can rewrite that as a power. So I would have w, I wrote it over here to the side, w to the 4th raised to the 1/2 power. Well, this would end up giving you w to the 2nd power. So I brought it back into the problem here. Then using the product rule, we can bring this together as a single logarithm. In this example here, it says solve the logarithmic equation. Well, in order to drop the logs, we would have to have the same base. So using the change of base formula on this portion, rewriting it in terms of base 2, we have log of the argument, 25, divided by log of the original base. Once again, in the denominator, this could simplify to just be 2. That 2 could be written in the front as 1/2 times this. That 1/2 could then be written as a power using the property, the power rule property. Remember, this then could be written as the square root of 25, which we know to be 5. All right. And then I could, now that I have the bases the same, single logarithm on both sides, I could drop the logs and say that the arguments are equal to each other, which again, x equals 25, x equals 5 is the final answer for me to turn in. Checking this, if you go back and put in a 5 where the x is, it keeps it greater than 0, and so we're okay to turn this in as our solution.